Swayam Prabha. Digital India. Educated India.
Welcome back to our lecture series on advanced hydraulics. We are in the fourth module on hydraulic jumps. If you recall, hydraulic jump means it is a type of rapidly varying flow where the depth of flow suddenly increases from a low depth to a greater depth. These things we had discussed it in the last class. In the last class, we had generally discussed on the theoretical aspects of the hydraulic jump. What are the various theories coming into picture? For example, we use the Reynolds transport theorem principle to evaluate the continuity and momentum principles for hydraulic jump. So, if you take the location of hydraulic jump in a controlled volume, how you can use the principles, continuity principle as well as momentum principles using the Reynolds transport theorem. If you recall them, from the continuity principle, we had easily arrived at this particular relationship that suggests that the discharge is same at upstream, that is pre-jump section as well as the post-jump section, the discharge will be same. From the momentum principle, we had observed that the specific force at the upstream and downstream of a jump are same. That is, in the jump, this is the upstream section, this is the downstream section, y 1, y 2. So, the specific force at this downstream upstream section as well as at this downstream section, both are same. So, the relationship of the specific force was given as such: A 1 h 1 bar plus q squared by g A 1 is equal to A 2 h 2 bar plus q squared by g A 2, where h 1 bar is the depth to the centroid in section 1, that is in the upstream section, depth to the centroid. Similarly, h 2 bar is also the depth to the centroid in section 2. We had discussed briefly on the rectangular channels, how we can analyze jumps in rectangular channels. In fact, we will be continuing with that portion today also. We have also studied the US Reclamation Bureau's mentioning about the types of jumps according to the Froude number. So, today we will be going through the characteristics of jumps in rectangular channels. So, the rectangular channel, whichever section you take, you can draw the two sections, that is one pre-jump section and this is post-jump section. So, jump means rise in water. So, here let us assume that the depth of water is y 1. Here let us assume that the depth of water it is y 2, y 2 greater than y 1. We have to analyze the characteristics now for the rectangular channel. So, what are the properties? You know the specific force at the pre-jump section as well as at the post-jump section, both are same, that is A 1 h 1 bar plus q square by g A 1 is equal to A 2 h 2 bar plus q squared by g A 2. Now, for the rectangular channel section, you know A 1 is equal to B y 1, A 2 is equal to B y 2, where B is the width of the channel, that will be same at the upstream and downstream sections of the jump. Then h 1 bar for the rectangular channel is nothing but y 1 by 2, h 2 bar is equal to y 2 by 2. So, incorporating all this relationship, what will we get? we will get the following relationship now, b y 1 squared by 2 plus q squared by g b y 1, this is equal to b y 2 squared by 2 plus q squared by g b y 2. Let us continue the simplifications. I am just taking b out now, that is b times y 1 squared by 2 plus q squared by g b squared, yes, it is q squared g y 1. This quantity is equal to, in the right hand side, b times y 2 squared by 2 plus q squared by g b squared y 2. So, you can cancel off b now in these portions, appropriately you can cancel off. Also, q by b, the quantity q by b in a rectangular channel section, say a rectangular channel section, it is carrying some discharge, right. So, this q by b quantity, it is a property of the channel now, q by b is equal to discharge per unit width of the rectangular channel. So, for a rectangular channel, it is a property. You can just define this quantity as a small q, so that we can use it in our equations and all. So, this entire equation will now become y 1 squared by 2 plus q squared by g y 1 is equal to y 2 squared by 2 plus q squared by g y 2, or you will get a relationship for q, small q, as follows: q squared by g into 1 by y 1 minus 1 by y 2, that is, we have taken it into the left hand side. These quantities you are taking it into the right hand side, y 2 squared minus y 1 squared. Continue the real, you can see that there are some common terms and all here. You will see this quantity becomes q squared by g into y 2 minus y 1 by y 1 y 2 is equal to half of y 2 squared minus y 1 squared. So, you know from your mathematics, a square, any two variables a and b, a squared minus b squared is equal to a minus b into a plus b, right. The same principles you are applying, logic you are applying, you are further simplifying the things. You will get q squared by g, this is equal to half of y 1 y 2 into y 1 plus y 2. Like this I will get a relationship. So, let me call this as equation 1. So, you may be using them for many analysis today, right. So, this relationship, that is the discharge per unit width of the channel, you are now relating it with the pre and post jump depths of water. Like that you are able to now correlate it. Just for your benefit, we can just if you recall, in the rectangular channel section, we had come up with a representation according to the upstream fluid number. We have came up with a relationship for the rectangular channel. We will see how it is arriving at now. The same equation, now we are going to rearrange it, that is y 1 into y 2 plus y 1 plus y 2. This is nothing but equal to twice q square by g, that is y 1 squared y 2 plus y 1 y 2 square minus twice q squared by g equal to 0. It is a quadratic form. You can represent the quadratic form either in terms of y 1 or y 2, as y 2 is the unknown term in most of the cases. We do not know what is the post jump depth, because pre jump depth we already have. It is V who is releasing the water either from sluice gate, or it is V who is allowing the spillway flow and all in the over spillways and all. So, we know the pre jump depth mostly. So, we want to identify the post jump depth. So, based on those manipulations, let me suggest this as now a quadratic form, means a quadratic equation in terms of y 2 or the post jump depth. So, this can be now rearranged as y 1 y 2 plus y 2 square minus 2 q square by g y 1 equal to 0. That is, I just divided it by y 1, or y 2 square plus y 1 times y 2 minus 2 q square by g y 1 equal to 0. You use your mathematics principles and all. So, you will get the solution for this quadratic equation. Y 2 is nothing but equal to minus y 1 plus or minus y 1 times root of 1 plus 8 q square by g y 1 cube by 2. Like this portion can be written. From that, I will be getting it in the following form. I can write it easily in this form. Recall the Froude number. So, Froude number in the upstream f r 1, we gave it as v 1 squared by g y 1, is not it? This is nothing but now q squared by g y 1 cube, because you know that is the flow per unit width, discharge per unit width q is nothing but equal to v 1 into y 1. This is again nothing but equal to v 2 into y 2. So, the same quantities will be using it. So, I am writing the Froude number in terms of discharge per unit width q squared by g y 1 cube. So, therefore, the above equation, this particular equation, this becomes y 2 by y 1 is equal to half times minus 1 plus or minus root of 1 plus say q squared by g y 1 cube. What is this thing? This is Froude number. So, 8 f r 1 square. So, we have already seen this relationship, that is we had at that time we have just briefly mentioned that you can relate the sequent depth ratio with respect to the Froude number, and this is how it is derived at. Let me give this as equation number 2. So, that is the sequent depth ratio relation upstream Froude number. Now, let me go through some of the characteristics of jumps. Some of the characteristics in the jumps. of course, we are dealing with the rectangular channels, as the heading means. This today's class is mainly on the rectangular channel, jumps in rectangular channels itself. So, the sequence depth relationship, as we are aware now, y 2 by y 1 is equal to half into root of 1 plus 8 f r 1 squared minus 1. This I can represent it in another form, 8 f r 1 squared raised to half minus 1. Like this also I can just write it. So, from this equation, you can, if one depth, if the pre-jump depth is, if it is given to you, you can easily identify what is the post-jump depth. There is no need to go and measure it in the means. If you are aware of the type of flow and all, you can easily now measure the quantities. First one for among the characteristics is about the energy principles. When you apply the energy principles, let me suggest you here in the flow in rectangular channels, while dealing with hydraulic jumps in rectangular channels and all. Hydraulic jump, you know that it dissipates energy, isn't it? It dissipates energy, means from the upstream whatever amount of energy is there, some quantity of energy gets lost. So, whatever change in energy is there, at present we are assuming that that change in energy is due to the change in specific energies at the upstream and downstream section. The other type of energy losses and all we are not taking into account here. Fine. So, we can compare the specific energies at the upstream and downstream first. So, specific energy at the upstream of the jump, we can give this as E 1 is equal to the depth of flow plus V 1 squared by 2 g. So, you know what is meant by specific energies. So, that specific energy at the pre-jump section, we can write it as follows. Just recall the hydraulic jump. So, at this section, what is the specific energy that is being measured? Now, at this is the post jump section, what is the specific energy there, that also can be suggested. At the downstream of jump, specific energy E 2 is equal to y 2 plus V 2 squared by 2 g. Just going back into the previous slide, if you recall V 1, the discharge per unit width, it was given as q is equal to V 1 into y 1. So, therefore, V 1 is nothing but q by y 1. So, that thing will be substituted here. I can write this as y 1 plus q squared by 2 g y 1 square. Similarly, for the upstream portion also, we can write the specific energy E 2. Now, this is equal to y 2 plus q squared by 2 g y 2 square. Therefore, change in energy in two sections. The change in energy in two sections, again I am reiterating that the hydraulic jump, say the two sections whichever we are taking into account, the reach of that section, it is small. So, we are considering that whatever change in energies at those two sections are there, it is due to the change in the specific energies at those sections. The other type of losses we are not taking into account again, because the reach of that hydraulic jump is too small. So, coming back into this thing, I can write the change in energy del E. This is equal to E 1 minus E 2. Naturally, E 1 is greater than E 2. You know that, otherwise the flow means you cannot accommodate the quantities, or hydraulic jump itself means it is dissipating the energy. So, I am just writing the quantities again here, q squared by 2 g y 1 squared minus y 2 minus q squared by 2 g y 2 squared. Like this I can easily write it, rearrange the terms. So, this becomes a change in energy del E. Now, this becomes y 1 minus y 2 plus q squared by 2 g into 1 by y 1 squared minus y 2 squared. Again y 1 minus y 2 plus q squared by 2 g y 2 squared minus y 1 squared by y 1 squared y 2 squared. Like this I can write the thing. From the equation 1 we had derived today, q squared by g is equal to half of y 1 y 2 into y 1 plus y 2. You recall them, right? You just substitute these quantities here. So, you will get an expression for del E now. So, I can write the quantity now, del E, this is equal to y 1 minus y 2 from here, this is y 1 minus y 2 into 1 minus q squared by 2 g y 1 plus y 2 by y 1 square y 2 square. So, you can write it in the other form also, that is, instead of writing y 1 minus y 2, you can write it in terms of y 2 minus y 1, because you naturally know that the hydraulic jump y 2 is the larger depth, y 1 is the smaller depth. So, to avoid the negative things and all, and also to give a more physical relevance, you can write it in terms of y 2 minus y 1. Also, you substitute the expression, this expression whichever is given to you, you substitute them here. So, I can write the quantity del E. Del E, this is nothing but equal to y 2 minus y 1 into y 1 plus y 2 whole square by 4 y 1 y 2 minus 1. Do I need to explain it? We are substituting this entire quantity in q squared by g. So, the q squared by g is equal to half of this quantity. So, here y 2 minus y 1 term is there, y 1 plus y 2, y 1 plus y 2, y 1 those things gets multiplied, and we are getting the square of those quantity. That is the reason it is coming into picture in this way. So, I can rearrange the quantities again, y 2 minus y 1 into y 1 plus y 2 whole square minus 4 y 1 y 2 by 4 y 1 y 2. Like this also I can write it. That is your simple cubic expansion of y 2 minus y 1 quantity. So, 1 by 4 y 1 y 2 into y 2 minus y 1 whole cube. So, this is the expression for change in energy. So, let me assign this as equation number 3. This is how you derive the change in energy term. If you want to express energy in terms of relative terms, you can say for example, if I express this quantity now, you can define a ratio del E by E 1. So, this is called relative loss of energy, because you know the upstream section energy, specific energy, and what is the energy loss. So, like that the non-dimensional form of loss in energy can be expressed. So, it is a relative loss in energy term. If you want to find it in terms of root number, that is also quite possible. You know that del E is now in terms of y 1 and y 2. Similarly, E 1 it is in terms of y 1. If you find their ratios, corresponding ratios, if you incorporate the corresponding relationship y 2 by y 1 is equal to half of 1 plus 8 f r 1 squared to the power of half minus 1. If this relationship, if it is incorporated in those ratios and all, you will get the relative loss of energy in terms of Froude number. That is also quite useful thing. So, efficiency of a jump. You can find the efficiency of a jump by identifying the ratio upstream specific energy by downstream specific energy. So, in the hydraulic jump, this is upstream quantity, whatever specific energy is there E 1, whatever specific energy is there in the downstream section E 2. So, E 2 by E 1, whatever change is there, what is that ratio, that is called the efficiency of hydraulic jump. So, you can easily write again, as I mentioned it earlier. For example, you know E 2 is equal to y 2 plus q squared by 2 g y 2 squared. So, this can be written as q squared by g is equal to half of y 1 y 2 into y 1 plus y 2. You incorporate this relationship here as well. So, I will get a corresponding form 1 by 4 y 2 square into 4 y 2 cube plus y 1 squared y 2 plus y 1 y 2 squared. Like this, I will get an expression for E 2 in terms of y 1 and y 2. Similarly, E 1 is equal to 1 by 4 y 1 squared into 4 y 1 cube plus y 1 squared y 2 plus y 1 y 2 squared. Like this you will get. So, their corresponding ratios. Therefore, E 2 by E 1 you will get the corresponding quantity 4 y 2 cube plus y 1 squared y 2 plus y 1 y 2 squared by 4 y 1 cube plus y 1 squared y 2 plus y 1 y 2 square into y 1 by y 2 whole square. Like this, I will get the corresponding, means that efficiency of jump relationship. The efficiency of jump, you can obtain it in the particular form. This again, as I mentioned earlier, you can express it in terms of Froude number, upstream Froude number, because you know that y 2 by y 1 is nothing but equal to half of 1 plus 8 f r 1 square, this quantity is rooted minus 1. If this quantity is substituted here, you can easily get the expression in terms of f r 1 square. Just for a simple demonstration, I can show it to you now. E 2 by E 1. For the other quantities, I expect from you to do the expansion and obtain the corresponding relationship and all. Just here also, I will not be deriving it up to the final step. I am just showing you how you incorporate the sequent depth ratio in the above efficiency relationship E 2 by E 1, and correspondingly you will get all the terms in that ratio in Froude number quantities. So, the jump efficiency ratio, it can be expressed, means as I mentioned earlier. Now, from the previous slide, if you guys have gone through this, the E 2 by E 1 term, I had expressed it in this following relationship. So, here for the y 2 term, we have just substituted from this particular relationship, what is y 2 that has been substituted here. Similarly, wherever y 2 is coming in picture, this relationship is substituted. Similarly, this y 1 by y 2 whole square, that is nothing but the inverse of this quantity, right. So, that is also being substituted there. So, like that we are incorporating the terms here, and I am getting the corresponding equation in the expanded form. So, here you will see that even these y 1 cube terms, these y 1, it is uniform everywhere, and that will also get cancelled out. So, you are getting this efficiency practically in terms of Froude number. So, like that you are able to derive this efficiency quantities and all. You can arrange, means for similarly for all the quantities, you can arrange the things. Next we can suggest is that height, next characteristics of the rectangular jump is height of the jump. You can think of height of the jump also. So, you have jump, this is pre-jump, this is post-jump depth. So, height of the jump h f or h j, whatever, just to avoid confusion, h j, let me write it, this is equal to nothing but y 2 minus y 1, it is a simple terminology. However, this height of the jump, this again can be represented in terms of some standard value, standard in the sense for this particular any rectangular channel, the specific energy of the upstream, that will be the maximum depth, means the specific energy it is possible, right. So, E 1 and y 1 are known quantities. So, if the ratio h j by E 1, if this quantity is obtained, then this quantity is called relative height of the jump. This is called relative height of the jump. So, this is a more useful value. Of course, we will see how it is useful, means we can just demonstrate them also. Again, this quantity relative height of the jump, this can be represented in terms of upstream fluid number FR1. So, I am not deriving that, you have already seen it for the efficiency how one can derive it these quantities. In a similar approach you can derive this quantity also. The relative height of the jump, it is a non-dimensional quantity, this is nothing but equal to 1 plus 8 FR1 square, the square root of this quantity minus 3 by FR1 square plus 2. Like this you can obtain the relative height of the jump as well. Why you are requiring these quantities? Why such quantities, non-dimensional quantities are being identified? We will see that, means it will be quite useful. Another quantity, non-dimensional quantity I can suggest is, say the change in energy was already mentioned. So, this change in energy with respect to the upstream energy, this is called the relative energy loss. So, you know del E is equal to y 2 minus y 1 whole cube by 4 y 1 y 2, right. Energy relationship you have already derived that. So, and E 1, this can also be expressed in terms of y 1 and y 2 that we have seen in the previous slide here. E 1 is equal, E 2 is equal, E 1 is equal to in terms of y 1 and y 2, that is also obtained. Substitute those quantities, you will again get this relationship del E by E 1 in terms of fluid number at the upstream section. So, again I am not going to derive it, you have already seen the derivation process. So, I will just write the final form 1 plus 8 FR1 square, the square root of this quantity minus 3 whole cube divided by 8 times 2 y's FR1 square 1 plus 8 FR1 square raised to half minus 1. So, if we have these ratios, these corresponding ratios in terms of the fluid number, upstream fluid number, then the suggestion is that the upstream fluid number is the only quantity you require. From that you can easily analyze the jump in the rectangular channels. What are the peculiarities of these quantities del E by E 1 as well as H j by E 1? I can just show some two plots here. You see here the first one, this corresponds to say the x axis is the fluid number and the y axis, this is the relative energy loss. It is the relative energy loss represented del E by E 1. So, if the fluid number, if it is slowly increased from 0 to 20, you can see the curve following the path in the following form, right. The path is being followed. So, you can see that at very large fluid numbers, that is fluid numbers of 20 and all, that will yield a considerable energy loss, that is del E by E 1, it is very high